So having just spent some time talking about limits involving infinity, I'd like to talk a little bit more about this concept of infinity. This idea that we're going to talk about now is going to lead us into something that we will do several weeks into the calculus portion of the class. So most fractions, if you take a real number other than 0, which is always a special case, and you divide it by itself, you always get 1. 5 over 5, 5 million over 5 million, negative 7 pi over negative 7 pi. They always give us an answer of 1. But what if you have a quantity that's going to infinity over, a quantity that's going to infinity, or maybe negative infinity, over another quantity that's going to infinity over negative infinity? Will these always be 1, or maybe negative 1 if you had positive for one of them and negative for the other? So does this infinity behave the way that other non-zero quantities behave? That when you divide it by itself, will you always get 1? So what do you think? Think about this for yourself now. Pause the video, see if you think it's always going to be 1. If it's not going to be 1, can you come up with an example where it's not 1? Well, how about this? Give me your favorite number. I think I heard 6. So let's try this example. So how about the limit as x goes to infinity of 6x squared plus 1 over x squared? So I hope you would agree that both the top and the bottom of this fraction are going to infinity. So this is one of these examples of infinity over infinity, the so-called indeterminate form that we've just discussed. But this one, unlike some that we're going to see later in the semester, is easily attacked with just basic algebra because I can divide this fraction up into two separate fractions. 6x squared over x squared, which just simplifies to 6, plus 1 over x squared. And now this is the sort of limit that we just did in the previous segment. You can draw a graph, or you can think about plugging in a really big value for x. When you do that, 1 over x squared will go to 0, so this whole thing will go to 6. So for those of you who said that 6 was your favorite number, which is a good choice, by the way, infinity over infinity, in this case, ended up being 6. And was there anything special about 6? If your favorite number had been 33, do you think we could have gotten 33 out of this? Sure. If your favorite number were negative 25.73, could we have gotten negative 25.73? Definitely. I would just replace this 6 by negative 25.73. What if your favorite number were 0? What could we do there? It's a good favorite number to have too, by the way. How about if we do something like x plus 1 over x squared? Again, I hope you will agree that the top and the bottom of the fraction are both going to infinity. So we again have one of these indeterminate forms, infinity over infinity. But again, I can do a little bit of algebra. And I get x over x squared, which simplifies to 1 over x. And I get 1 over x squared, which is just 1 over x squared. And as we saw in the graphs before, both of these quantities, as x gets very, very large, both of these quantities go to 0. So in this case, the infinity over infinity ended up being 0. What if your favorite, I won't call it a number, what if your favorite concept is infinity? Could we get an answer of infinity out of this? So we already know how to get any real number that we like, positive or negative here. And this tells us how to get 0, which is also a real number. So these two ideas together give us all the real numbers. Can you come up with a way to get infinity? And I think we can. If we do, say, x cubed plus 1 over x squared. Again, the top and the bottom are both going to infinity. I hope you'll agree. But again, I can do a little bit of algebra. And I get x cubed over x, which just gives me x, plus 1 over x squared. And when x goes to infinity, this part goes to 0, as we've seen several times. But this part is getting very, very huge. So this would go to positive infinity. So the fact is that this indeterminate form, positive infinity, plus or minus infinity over plus or minus infinity, can end up equaling any real number or infinity or negative infinity. Indeterminate form can result in any real number, including 0, or infinity, or negative infinity. So I hope this convinces you that infinity is not a number. Because if in infinity were just any old normal number, when you divide it by itself, and since infinity is not 0, you should get 1. We can get any number we want. And we will see these sorts of indeterminate forms coming up again later. And then we'll have a different approach to deal with them when we have calculus, when we can't do them with such simple algebra as this. And the reason that they're called indeterminate forms is that most fractions, when you look at them, you can see what they are right away. 8 over 2 is always 4. 3 over 12 is always 1/4. Those are determinate forms. There's no doubt about them. However, when you get infinity over infinity, you need to do some more work in order to determine what its value is. And that's why this is called an indeterminate form. By the way, the reason that I said that whoever picked 6 out there made a very good choice is that 6 is a so-called perfect number. And a perfect number is a number whose proper divisors, so the numbers that divide it, that are factors of it, that don't include itself, add up to it. So what are the proper factors of 6? They are 1, 2, and 3. And look at that. When you add them up, what do you get? 6. Another perfect number is 28, because its factors are 1, 2, 4, 7, and 14. And when you add those together, you get 28. And people have been fascinated with these perfect numbers through history. The next one, don't know what the factors are, but the next one bigger than that is 496. And I believe the one after that is 8,128. So they are quite rare. And nobody has ever found an odd one. So you'll notice that the first 4, the smallest 4, are all even numbers. Nobody has ever found an odd one, and nobody has ever proved that there isn't an odd one. So this is one of these open questions in math that's a very simple question to state, and yet it has just baffled the greatest mathematicians for ages. So that's something for you to work on in your spare time. This symbol infinity was first used in 1655 by this mathematician named Wallis, and nobody's really positive where it came from. One idea is that it came from the Greek letter omega, which sort of looks like an infinity symbol. And why would, of all the Greek letters, would they choose omega? Omega is the last Greek letter. So if you ever heard the expression from alpha to omega, alpha is the first Greek letter, omega is the last Greek letter. So some idea that this is representing some very, very big number. Another possibility is that it came from Roman numerals, where apparently one way of writing 1,000, I think often today we see 1,000 written as M, but an old way of writing 1,000 was a C with a D next to it. And again, you can sort of imagine combining those two together, like with the omega symbol, and you get something that looks like infinity. And I guess back in those days, 1,000 was considered a big number. One last thing about infinity. There's this imaginary hotel called the Hilbert Hotel, where there is a room in the hotel that on the door has any real number, any positive integer you can think of. So there's a room 6, there's a room 28, there's a room 8,128, there's a room 8675309. It's got that on the door. Any number you can think of, positive integer, there's a door that has that number on it. If you're assigned to that room, you can find that room. So one night, very late at night, you're very tired, you show up at this hotel, and the clerk at the desk says, "Oh, I'm sorry, sir, all of the rooms are full." But you don't want to go and try to find another hotel. So what can you suggest the clerk do so that nobody is too inconvenienced? In other words, nobody has to move more than one room, more than one time, that is. But everybody will still get a room, nobody will have to share, and you'll get a room. So think about this for a second. Pause the video if you would like. Remember, every room is already occupied. So it's not as though you can somehow say, "Oh, I'm going to go to the last room." Because there is no last room, because there is no biggest positive integer. The positive integers go on and on forever. So the solution is that you suggest that the person who's currently in room 1 should move to room 2. And the person who's currently in room 2 should move to room 3. And I think you see where the pattern is going to go here. And the person who's in room 1,000 will move to 1,001, and so forth. So everybody still has a room, right? And nobody had to share with somebody they weren't sharing with already. But what room is now open? Room 1 is now open, and that's the room that you take. So even though every room was full, you managed to find an open room that didn't involve anybody switching rooms more than once. So that's impressive. You should be a little astounded at this idea of infinity. How about this, though? Another night you show up at the hotel, and it's not just you, but it's you and your infinitely many friends, all showing up in a long succession of buses. And you all want rooms, and you don't want to share it all. Maybe you're not that good of friends, but you don't want to share it all. And again, the clerk tells you that every room is full. What can you do so that nobody has to change rooms more than once, everybody gets a room, nobody has to share? And it's not going to work the same thing, right? You can't just say, oh, let's have everybody shift over 1 million, because you have more than 1 million friends. You have infinitely many friends. So just having everybody add 1 million to their room number, that'll give rooms for 1 million of your friends, but you still have infinitely many more friends with no rooms. Somehow you have to create infinitely many spaces without making anybody move more than once. So this is a good question. And again, if you're interested in it, you should pause the video and really give it some serious thought now. Here's the way to do it. The person in room 1 moves to room 2. The person in room 2, we can't have them move to room 3, right? That's not going to work. The person in room 2 moves to room 4. The person in 3 moves to room 6, 4 to 8, 5 to 10. In other words, everybody moves to twice the room that he or she is currently in. So now all the rooms that are occupied are even numbered, meaning what rooms are all now unoccupied? Every odd number. And how many odd positive integers are there? There are infinitely many odd positive integers. So you can take room 1, your next friend can take 3, then 5, 7, 9, 11. Your infinitely many friends all have a room each to yourself. So this is named the Hilbert Hotel because it was come up with by the mathematician David Hilbert as just a way of exploring the seeming contradictions of infinity. Infinity is just full of surprises. You can spend years and years studying all different sorts of infinities. And I enjoy it, as I hope you can tell, and I hope that you enjoyed that too.